Tonight, we're going to talk about a planet that human beings have been staring at, up close, with spacecraft, for nearly half a century. A planet visited by 5 separate missions. A planet watched continuously, in obsessive, loving detail, for 13 unbroken years by a single orbiter that circled it more than 200 times before finally, deliberately, diving into its clouds and burning up as a final act of scientific devotion. A planet that, by any reasonable measure, we should understand better than almost anything else in the solar system that isn't our own home. And here's what most people don't realize. In the last few years, the most powerful space telescope humanity has ever built pointed its instruments at that exact planet, the one we thought we already knew, and came back with results that made working scientists say something you almost never hear in a peer-reviewed paper. Not, "This refines our model." Not, "This confirms what we suspected." The actual words on the record from the researcher who led the study: completely unexpected and completely unexplained. Not once, multiple times. Multiple separate, independent mysteries arriving from the same single stretch of observation. This isn't the kind of scary that involves a monster or a threat. It's a quieter, stranger unease. The specific feeling of watching some of the most qualified scientists alive, working with the most sensitive instrument ever pointed at the sky, look directly at something we've already studied for 46 years and simply not know what they're looking at. The first surprise is a string of dark, unexplained patches embedded in Saturn's glowing aurora, stable for hours, then drifting, behaving in a way nothing in existing atmospheric science predicted. The second surprise, found in the very same observation, is a star-shaped pattern hundreds of kilometers below those dark patches. A structure that should have 6 arms, symmetric with the famous hexagon deep in Saturn's clouds, and instead has only 4, with 2 simply missing for reasons nobody can currently explain. The third surprise is a 45-year-old mystery about the planet's own basic rotation. Something that sounds like it should have been settled decades ago, that was only just solved using this same data, and which immediately handed scientists a brand new anomaly to replace the one they'd finally closed. And the fourth surprise is what's happening on one of Saturn's own moons, a jet of water taller, relative to its source, than almost anything else observed anywhere in the solar system, potentially hiding the chemistry of life itself. By the end of tonight, you're going to understand exactly what James Webb found when it turned its eyes towards Saturn, not as a completed discovery with a tidy explanation, but as an honest, ongoing, still unfolding scientific mystery, unfolding in real time on a planet we thought we already knew everything important about. Before we dive in, if you're someone who finds real comfort in sitting with the universe's open questions, who trades the noise of the day for a little cosmic perspective before sleep, consider liking this video or subscribing to the channel. It's a small thing, but it helps us keep making this kind of content for people who share that same quiet curiosity. Now, let's begin. Let's be honest about what we mean by scary tonight, because it isn't what you might initially assume. This isn't a story about danger. Saturn poses no threat to anyone. It sits, as it always has, nearly 900 million miles from Earth, a gas giant with no solid surface, ringed in ice, entirely indifferent to whatever we discover about it. The unease this story carries is a different, quieter kind. The specific, genuine discomfort of watching modern science, at the absolute height of its technical capability, come face to face with its own limits. Most of what a telescope like James Webb finds, when it looks at a well-studied object, does something reassuring. It refines. It sharpens an existing picture, adds detail to a model scientists already largely trust, confirms a suspicion that's been circling for years. That's the normal rhythm of planetary science. Steady, incremental, comforting in its predictability. Saturn, in 2025 and 2026 specifically, did not follow that rhythm. A team of researchers studying its atmosphere publishing their results in a respected peer-reviewed journal, described what they found using language you almost never see in that kind of paper. Completely unexpected and, at present, completely unexplained. A separate team working through a genuinely different puzzle, one that had quietly persisted, unsolved, for over 4 decades, needed until 2026 to finally close the case, using data gathered in 2024. And a third group, studying the raw physics of Saturn's own winds, stated plainly, in their own published words, that there is as yet no theory capable of explaining the nature of the stream they were measuring, nor the source of the energy feeding it. Here's why that specific combination of facts matters. Saturn is not some newly discovered, barely glimpsed object at the edge of the solar system. It has been observed by spacecraft since 1979. It was studied intensively, continuously, for 13 straight years by one of the most successful missions in the history of space exploration. It is, by any reasonable standard, one of the most thoroughly examined objects that isn't our own planet. And it is still, right now, tonight, capable of handing working scientists a result they genuinely cannot explain. That's the quiet, real unease at the center of tonight's story. Not a monster, not a threat. Just the humbling, honest experience of looking as closely as we currently know how to look at something we already thought we understood and discovering that we don't. Not entirely, not yet. To understand exactly how surprising Webb's discoveries actually are, we first need to understand how much we already knew. Because the baseline here is genuinely extraordinary, and it makes what comes later considerably more striking by comparison. Cassini launched from Earth in October 1997, beginning a journey that would take nearly 7 years to reach its destination. It arrived at Saturn on July 1st, 2004, and would remain there, orbiting continuously, gathering data without interruption for 13 full years. One of the longest sustained scientific observations of a single object in the entire history of space exploration. Its mission finally concluded on September 15, 2017, in a moment that has become something close to legendary among planetary scientists. Rather than simply letting the spacecraft drift indefinitely, engineers deliberately steered Cassini into Saturn's own atmosphere, sending back data for as long as physically possible before the immense heat and pressure of the planet's own clouds tore it apart. Mission controllers called it the grand finale, a spacecraft, having spent 13 years faithfully studying a planet, finally becoming part of it. Cassini did not travel alone. It carried with it a smaller probe named Huygens, built by the European Space Agency, which detached from its parent spacecraft and descended through the thick, hazy atmosphere of Saturn's largest moon, Titan, landing safely on its surface on January 14, 2005. At the time, it represented the most distant landing any human-made object had ever achieved. A genuine milestone in the history of exploration, occurring on a moon so alien in its chemistry that its rivers and lakes are made not of water but of liquid methane and ethane. Across its 13 years at Saturn, Cassini built the entire scientific baseline that everything in tonight's story now builds on top of. It imaged, in unprecedented, obsessive detail, a genuinely bizarre feature at Saturn's North Pole, a persistent, six-sided jet stream, shaped with almost mathematical precision into a hexagon, first glimpsed decades earlier by the Voyager spacecraft, but only truly understood through Cassini's years of continuous observation from 2006 through 2017. On October 11, 2006, it discovered something entirely different at Saturn's opposite pole. Not a hexagon at all, but a hurricane-like vortex with a clearly defined eye, structurally unlike anything at the north, a difference that remains, even now, one of the genuinely unsolved puzzles of the entire solar system. And in 2005, almost immediately after arriving, Cassini detected something that would eventually reshape our entire understanding of where life might exist in our own solar system. Active plumes of water ice, erupting continuously from the small, icy moon Enceladus. A discovery that, over the following decade, led directly to confirmation of an entire subsurface ocean hidden beneath that moon's frozen crust. Even Cassini's own instruments had, buried within their data, an early hint of a mystery that wouldn't be solved for another 20 years. As far back as 2004, the spacecraft's thermal infrared instrument had recorded something strange in how Saturn's rotation appeared to behave. Readings that didn't quite make sense, filed away as an open question, waiting patiently for an instrument sensitive enough to finally resolve it. This is the baseline. 13 years of continuous, world-class observation. A hexagon mapped in extraordinary detail. A second, different vortex discovered at the opposite pole. An entire ocean-bearing moon identified. And, quietly, one strange rotational anomaly, noticed but not yet understood, left sitting in the data, waiting for whatever came next. Here's a detail about the transition from Cassini to Webb that rarely gets mentioned, and it matters more than it might initially seem. When Cassini burned up in Saturn's atmosphere in September 2017, humanity's closest, most detailed eyes on the planet went dark. For the following 5 years, the only available views of Saturn came from Earth-based telescopes and the aging but still capable Hubble Space Telescope. Both genuinely useful instruments, but nothing close to the intimate, continuous, close-range observation Cassini had provided for over a decade. Saturn simply sat there, orbiting the Sun, changing with its seasons, largely unwatched at any real level of detail for half a decade. James Webb's first dedicated observations of Saturn didn't arrive until November 2022. A genuine 5-year gap in humanity's close scientific attention to the planet. And that gap matters for a specific reason. Saturn takes 29.4 Earth years to complete a single orbit around the Sun, which means its seasons unfold at an almost glacial pace compared to our own. By the time Webb finally turned its instruments towards Saturn in late 2022, the planet had drifted meaningfully further along in its own multi-decade seasonal cycle than anything Cassini had ever directly observed. Some of what Webb would go on to find wasn't merely new. It was, in a very real sense, the first update to Saturn's atmospheric record in 5 years, captured at a point in its seasonal cycle no spacecraft had ever examined this closely before. That first Webb study used an instrument called MIRI, the mid-infrared instrument, capable of observing wavelengths of light stretching from about 4.9 to 28.8 microns, a range that had never before been used to map Saturn's full disk in this kind of resolution. Cassini had carried a comparable infrared instrument of its own, called CRS, but it functioned as a lower-resolution spectrometer rather than a true high-detail imager. Webb's MIRI observations, led by Professor Lee Fletcher of the University of Leicester and published in 2023, represented something genuinely new, the sharpest infrared portrait of Saturn's atmosphere ever assembled. But actually capturing that portrait turned out to be far more technically demanding than it might sound. And the specific difficulty is worth understanding, because it reveals something honest about the limits of even our most advanced instruments. James Webb was built, first and foremost, to stare at extraordinarily faint, extraordinarily distant targets. Galaxies so far away their light has been travelling for over 13 billion years, points of light so dim that capturing them requires extremely long, patient exposures. Saturn is the opposite kind of target entirely, bright, large in Webb's field of view, and rotating once every 10 hours and 42 minutes. Fast enough that a single long exposure, of the kind Webb was designed for, would simply blur the planet's surface detail into an unusable smear. Observing Saturn properly required an entirely different approach. Shorter, carefully sequenced exposures, individually timed, and then digitally stitched together into a single coherent image. And even with that workaround, the original 2022 observing plan, designed years earlier, before Webb had even launched, based on an assumption about when the telescope would actually reach space, had hoped to catch a very specific geometric alignment, the the 6 precise corners, or vertices, of Saturn's famous hexagon, captured directly in thermal infrared light. By the time Webb actually launched, and actually reached the point in its schedule where it could observe Saturn, that specific geometric alignment had already passed. Researchers involved in the project noted, with a kind of re-signed scientific patience, that the next opportunity to directly image the hexagon's vertices this same way won't arrive again until the 2040s. Sit with that for a moment. An instrument capable of photographing galaxies from the dawn of the universe missed its own planned window to photograph 6 specific points on a planet in our own solar system by a matter of months, and will now have to wait roughly 20 years to try again. Following that initial 2022 MIRI study, Webb returned to Saturn with additional instruments. In June 2023, its NIRCam camera captured new images revealing what researchers described, in their own words, as structures never before seen. And on November 29, 2024, NIRCam imaged Saturn again. On the exact same day as a separate, far more consequential observation, made with a different instrument entirely, that would go on to produce 2 of the most genuinely strange discoveries in this entire story. Here is where tonight's central mystery actually begins. On November 29, 2024, James Webb's NIRSpec instrument, the near-infrared spectrograph, a different tool entirely from the MIRI camera used in 2022, conducted a single, continuous observation of Saturn lasting 10 full hours. 10 hours happens to be almost exactly 1 complete Saturn day, meaning this wasn't a brief glimpse. It was a full rotational cycle of the planet, watched without interruption, capturing an entire day of Saturn's atmospheric behavior in one unbroken sweep of data. What emerged from that 10-hour observation, once researchers had processed and analyzed it, was something nobody had predicted, and nobody, even now, has fully explained. Embedded within Saturn's bright auroral rings, the glowing curtains of light produced when charged particles from the Sun collide with the planet's upper atmosphere near its magnetic poles, the same basic phenomenon that produces the northern and southern lights here on Earth, but on a scale suited to a planet many times our size. Researchers found a chain of dark, bead-like patches, not scattered randomly, but arranged in a distinct pattern, spread across a band of latitude roughly between 55 and 65 degrees north, sitting at an altitude of approximately 1,100 kilometers, or about 680 miles, above Saturn's cloud tops. High up, deep in the planet's ionosphere, the electrically charged uppermost layer of its atmosphere. Here's what makes them genuinely strange, rather than simply unexpected. Individual dark beads remained remarkably stable, holding their position for hours at a time. And yet, across the full 10-hour observation, they slowly drifted, shifting by a few degrees of longitude as Saturn rotated beneath them. They weren't a fixed, permanent feature, locked rigidly in place. They also weren't chaotic, random noise, appearing and vanishing unpredictably. They occupied a strange, specific middle ground, structured enough to be clearly real, patterned features, and mobile enough to defy any simple, static explanation. The research team behind this discovery, led by Professor Tom Stallard of Northumbria University, working alongside 23 scientists from institutions across the United Kingdom, the United States, and France, presented their findings at a major planetary science conference in Helsinki in September 2025, with the full study published in the journal Geophysical Research Letters. And Stallard's own assessment of what they'd found, given directly and on the record, captures the moment with real precision. These properties, he said, were completely unexpected and, to date, are completely unexplained. Picture a long string of holiday lights wrapped around something enormous, most of the bulbs glowing steadily, exactly as expected, but scattered among them, for no evident reason, a handful stay dark for hours at a stretch, occasionally shifting position slightly along the length of the string, defying every attempt by anyone examining the wiring to explain why those specific bulbs, and not others, keep going quiet. That's close to the actual observational experience researchers are describing here. Not an absence of light in general, but a very specific, structured, patterned absence, embedded within a field that, according to every existing model of how Saturn's aurora should behave, ought to be far more uniform than this. One hypothesis currently under active investigation involves turbulence. The idea that powerful winds, moving at different speeds at different altitudes within Saturn's atmosphere, might shear against one another where those layers meet, creating ripple-like disturbances at the boundary, in roughly the same way turbulent patterns form where two ocean currents of different temperature and speed collide, and mix along their shared edge. It's a genuinely plausible mechanism, grounded in real atmospheric physics. But it's worth being honest about exactly where this idea currently stands. It remains an early, proposed hypothesis, not a confirmed explanation. The research team, as of the most recent published work, has not settled on a mechanism they consider proven. This is shocking discovery number one, and it deserves to sit with you for a moment before we move any further. A chain of dark, structured, slowly drifting patches embedded in the aurora of a planet humanity has studied for nearly half a century, found using an instrument capable of resolving details no previous spacecraft could ever have detected, and, even now, completely unexplained by anyone who has looked at the data. To really understand why this particular mystery is genuinely difficult rather than simply unfamiliar, it helps to understand what an aurora actually is, and why scientists generally expect it to behave in a fairly predictable way. An aurora, on any planet with a magnetic field, forms through essentially the same basic mechanism: charged particles, mostly electrons and protons, streaming outward from the Sun as part of the solar wind, or in Saturn's case, also generated internally by interactions with its own moons and rings, get captured and funneled by the planet's magnetic field lines. Those field lines act like enormous, invisible highways, channeling the charged particles down toward the planet's magnetic poles, where they collide with atoms and molecules in the upper atmosphere. Those collisions excite the atmospheric particles, causing them to briefly absorb energy and then release it again as light. The glowing curtains and rings we recognize as an aurora. Because this process is governed by the planet's magnetic field, a large-scale, relatively smooth, well-understood structure. Auroras are generally expected to behave with a fair degree of overall consistency and symmetry. There can be genuine variation. Certainly, brightness can fluctuate, the exact shape can shift somewhat, particularly during periods of intense solar activity. But an aurora is not typically expected to develop discrete, individually stable, slowly drifting dark patches holding their position independently for hours before shifting, embedded within an otherwise continuously glowing ring. That specific combination, individually stable yet independently mobile, embedded within a structure governed by a large-scale, relatively smooth magnetic field, is what makes the dark beads genuinely puzzling, rather than simply a new detail added to an already understood picture. Whatever is creating them appears to require some additional, smaller-scale physical process, operating on top of Saturn's basic magnetic field structure, localized enough to produce individual, semi-independent features, yet persistent enough for each feature to remain stable for hours before it begins to move. This is precisely why the turbulence hypothesis, wind shear between atmospheric layers moving at different speeds, is being taken seriously as a starting point for further investigation. It's one of the few mechanisms in atmospheric physics capable of producing exactly this kind of localized, semi-stable, slowly evolving structure without requiring some entirely new, undiscovered physical process. But even if that hypothesis eventually proves correct, a second question immediately follows it, and it's a question nobody has yet answered. What, specifically, is driving winds powerful enough at that particular altitude, in that particular part of Saturn's atmosphere, to produce this exact pattern? The turbulence hypothesis doesn't fully resolve the mystery so much as it relocates it one layer deeper. And as we're about to see, that same November 29th, 2024 observation revealed a second mystery, sitting just a few hundred kilometers below the first. One that may, or may not, turn out to be directly connected to it. Roughly 500 kilometers, or about 310 miles, below the dark beads. Dropping down from Saturn's ionosphere into its stratosphere, a genuinely different layer of atmosphere, governed by different physics entirely. The same near-spec observation revealed something else, something arguably even stranger, a star-shaped pattern centered on Saturn's north pole, with distinct dark arms extending outward from the polar region toward the equator. Based on everything scientists already understood about Saturn's atmospheric structure, specifically the six-sided symmetry of the hexagon deep in the clouds below, researchers expected this newly discovered star pattern to display 6 matching arms, aligned with the hexagon's 6 corners. They found 4. 2 of the expected 6 arms simply are not there, and the research team currently has no explanation for why. The 4 visible arms do appear to align, geometrically, with corners of Saturn's hexagonal jet stream far below. A genuinely striking spatial correlation, suggesting some kind of connection reaching across hundreds of kilometers of atmosphere through completely different physical regimes. From the deep, cloud-level troposphere where the hexagon lives, up through the stratosphere where these star arms appear, and potentially further still, up into the ionosphere where the dark beads sit. But why only 4 of the expected 6 arms are visible, and why those specific arms appear to be flowing toward the equator rather than remaining fixed, are questions the research team has explicitly stated they currently cannot answer. The official press materials released alongside this discovery describe the state of scientific understanding, as of September 2025, in refreshingly direct terms. It is unknown why the dark arms are flowing towards the equator, or why 2 of the arms are missing. Here's why this particular finding matters beyond its novelty, beyond simply being one more strange pattern to add to the list. If the star arms really are connected to the hexagon's 6 corners, if energy, or structure, or some physical influence is genuinely traveling upward from the hexagon, through the stratosphere, and potentially into the ionosphere where the dark beads live, that would mean Saturn's atmosphere is vertically coupled across an enormous range of altitude and physical conditions in a way that has never been directly demonstrated before. Not a series of independent, layered phenomena, each behaving according to its own local physics. A single, connected system, somehow linking conditions in the deep, cloud-forming troposphere to conditions in the high, radiation-exposed ionosphere hundreds of kilometers apart through layers of atmosphere governed by entirely different physical rules. It's genuinely important to be honest about exactly how confirmed this idea currently is, though, because it's tempting to treat a striking spatial alignment as proof of a mechanism. It is not. The vertical coupling interpretation remains, explicitly, the research team's working hypothesis, their best current guess at what's connecting these layers based on the geometric alignment they've observed, rather than a confirmed physical mechanism they've actually traced and verified. To feel the actual scale of what's being proposed here, it helps to translate these altitude differences into something more familiar. 500 kilometers. The vertical gap between the dark beads and the star arms alone is roughly the distance separating Los Angeles from Las Vegas or London from Edinburgh, and the full span from the hexagon, down in the visible cloud layer, up through the star arms in the stratosphere, to the dark beads in the ionosphere, covers something like 1,600 kilometers of altitude in total, more than the driving distance across the entire state of Texas, laid out not across the ground, but straight upward through the atmosphere of a single planet. This is shocking discovery number 2. A second, separate mystery found in the exact same observation as the first, hundreds of kilometers away in altitude, hinting at a connection between Saturn's deepest visible clouds and its outermost charged atmosphere that no one has ever directly confirmed. and missing two arms that, by every existing model, simply shouldn't be missing at all. It's worth spending real time understanding why the idea of Saturn's atmosphere being vertically coupled across such an enormous range of altitude is such a genuinely significant and genuinely uncertain claim, rather than simply an interesting detail to note in passing. Planetary atmospheres are typically understood, layer by layer, as somewhat distinct physical regimes, deep in the troposphere. The lowest layer, where Saturn's visible clouds form, and where the hexagon itself lives. The dominant physics involves convection, pressure, and the movement of gas driven largely by heat rising from the planet's own interior. Higher up, in the stratosphere, temperature and pressure behave differently, and the dominant dynamics shift accordingly. Higher still, in the ionosphere, the physics changes again entirely. This is the layer where incoming charged particles, arriving from the sun or funneled in by the planet's own magnetic field, ionize the surrounding gas and where auroral processes, including, apparently, the dark beads, actually occur. Each of these layers is typically studied and typically modeled somewhat independently because the physical processes governing them are genuinely different. A wind pattern in the troposphere doesn't automatically imply anything specific is happening 1,000 kilometers higher in the ionosphere, any more than weather patterns near the ground on Earth directly dictate the specific behavior of our own planet's aurora. Finding a star-shaped pattern in the stratosphere whose 4 visible arms happen to align, geometrically, with the 6 corners of a completely different structure. The hexagon, sitting hundreds of kilometers below in the troposphere, is therefore a genuinely notable observation. It suggests these layers aren't as independent as conventional models generally assume. Something about the hexagon's structure, or the forces that create and sustain it, may be propagating upward through the stratosphere and potentially influencing conditions high in the ionosphere as well. But suggesting a connection and confirming the actual physical mechanism responsible for it are two very different scientific claims. A geometric alignment could reflect a genuine, causal, physical link between these layers. It could also, in principle, reflect a coincidence. Two separate phenomena, driven by entirely different underlying causes, that simply happen to share a similar spatial pattern by chance. Distinguishing between these two possibilities requires considerably more evidence than a single 10-hour observation can provide, however striking that observation's initial findings might be. This is precisely why the research team's own language remains so carefully hedged. They have found a genuinely intriguing spatial correlation. They have not yet confirmed the mechanism connecting it, and the 2 missing arms, a detail that doesn't fit cleanly into even the working hypothesis of vertical coupling, remain, for now, simply unexplained. Before we go any further into the newer discoveries this story is really about, it's worth spending real time with the hexagon itself, because it's the structure everything else in tonight's story keeps circling back to, and because its own history is stranger and less settled than most casual mentions of it suggest. The hexagon was first glimpsed during the Voyager 1 and Voyager 2 flybys of Saturn in 1980 and 1981. A genuinely bizarre discovery at the time, a 6-sided geometric pattern of clouds, sitting almost impossibly precisely at Saturn's north pole, holding its shape rather than dissolving into the kind of chaotic turbulence you might expect from any large-scale planetary weather pattern. Cassini's 13 years of continuous observation, from 2004 to 2017, allowed scientists to study it in far greater detail than the brief Voyager flybys ever could. As of the most recent 2025 James Webb observations, the hexagon has now persisted, continuously, for at least 45 years of documented observation. And there is no particular reason to believe it hasn't existed for considerably longer than that. It simply took until 1980 for a spacecraft to arrive close enough to actually see it. The scale of it is genuinely difficult to hold in your mind properly. The hexagon spans somewhere between 20,000 and 30,000 kilometers across, each of its 6 sides measuring approximately 14,500 kilometers in length. For direct comparison, Earth's own diameter is 12,742 kilometers. A single side of Saturn's polar hexagon is longer than the entire width of our planet. The jet stream that forms its 6 precise edges moves at approximately 320 kilometers per hour, or 200 miles per hour. A sustained, permanent wind speed, not a gust, holding its hexagonal shape continuously for at least 45 years. At the hexagon's center sits a churning polar vortex, roughly 2,000 kilometers or 1,250 miles wide. More than 50 times the size of a typical hurricane's eye here on Earth. Between 2012 and 2016, Cassini watched the hexagon's color itself shift, gradually, from a pale blue to a warmer gold, tracking Saturn's own multi-decade seasonal cycle as sunlight slowly returned to its northern hemisphere after years of winter darkness. A genuinely beautiful piece of direct observational evidence that this structure isn't static or frozen, but responds, in its own way, to the same basic astronomical rhythms that drive seasons here on Earth, just stretched across a period of years rather than months. And here is the detail that makes the hexagon a genuine, ongoing scientific puzzle in its own right, rather than simply a striking visual curiosity. Saturn's south pole has no hexagon at all. Instead, when Cassini turned its instruments toward the opposite pole in October 2006, it found something structurally different entirely. A hurricane-like vortex with a clearly defined eye and wind speeds reaching approximately 550 kilometers per hour or 350 miles per hour, considerably faster than the hexagon's own already impressive 320 kilometers per hour. Two poles on the exact same planet, subject to the exact same basic rotation, the exact same basic gravity, the exact same basic atmospheric composition, and yet producing two entirely different large-scale structures. Multiple independent sources describe this specific asymmetry as one of the genuinely significant unsolved puzzles in all of solar system science. Scientists have proposed real, serious theoretical models attempting to explain how the hexagon itself actually forms, though even here, genuine scientific consensus remains elusive. In 2015, a fluid dynamics model developed by researcher Raul Morales-Juberius at New Mexico Tech demonstrated, mathematically, how a fast-moving jet stream, interacting with slower-moving turbulent eddies surrounding it, can naturally lock into a stable, standing hexagonal wave pattern. A genuinely elegant piece of physics, directly analogous to certain kinds of wave behavior that can be produced and studied in laboratory fluid experiments here on Earth. Then, in 2020, a separate research team at Harvard proposed a meaningfully different explanation, tracing the hexagon's underlying origin instead to deep convection currents, churning far below the visible cloud layer, driven by heat rising up from Saturn's own interior. These are not the same explanation. Neither has been universally accepted by the wider scientific community as the definitively correct final answer. The hexagon's precise formation mechanism, even after 45 years of study, remains an actively researched question rather than a settled fact. There's one more piece of timing worth including here, because it adds a genuine sense of urgency to everything we've covered so far. As of Saturn's most recent equinox, in May 2025, the hexagon began moving into seasonal autumn darkness, meaning the November 2024 James Webb observation that produced the dark beads and the star arm discoveries may represent close to the very last clear, well-lit view of the hexagon available to any instrument for years to come, until that same pole eventually rotates back into sunlight, deep into Saturn's own multi-decade orbital cycle. And there's a genuinely elegant connecting thread linking the hexagon directly back to the mysteries we've already covered tonight. The hexagon's own 6 corners rotate around Saturn's pole at very nearly the planet's own overall rotational rate, which brings us directly to a mystery that sounds, on the surface, like it should have been the simplest thing in the world to measure. Here's a question that sounds almost embarrassingly basic. How fast does Saturn actually spin? For a solid, rocky planet like Earth, this question has an easy, precise answer, because you can simply track a fixed feature on the surface and time how long it takes to return to the same position. Saturn offers no such convenience. It has no solid surface at all. Simply layer upon layer of gas and cloud, all moving at different speeds relative to one another, with no single fixed point anyone could track directly. For decades, scientists relied on an indirect method instead, tracking radio wave emissions generated deep within the planet by its own internal magnetic field, and using the timing of those emissions as a proxy for the planet's true underlying rotation rate. This approach worked reasonably well for other gas giants. For Saturn, it produced something genuinely strange and genuinely troubling. Once scientists started paying close attention, the measured rate appeared to change over time, not by a small margin easily attributable to measurement error, but by an amount that, if taken at face value, would mean Saturn's own bulk rotation was speeding up and slowing down on timescales of mere years or decades. Something that, according to everything else we understand about planetary physics, simply should not be physically possible for an object of Saturn's size and mass. This apparent contradiction first showed up in data going all the way back to the Voyager flybys of the early 1980s, and it deepened considerably once Cassini began systematically tracking the signal from 2004 onward. For years, it sat as one of the genuinely unresolved oddities of Saturn science. Not ignored, but also not solved. In 2021, Professor Tom Stallard's team, the same researcher who would later lead the dark beads discovery, proposed a genuinely clever reframing of the entire problem. Saturn itself, they argued, almost certainly wasn't actually changing its rotation speed at all. Instead, the electrical radio signals scientists had been using as their proxy for rotation were themselves being distorted in a consistent but variable way by high-altitude winds moving through Saturn's ionosphere. The apparent changing rotation rate wasn't really about Saturn's rotation changing. It was about the measuring signal itself being pushed around by winds nobody had yet directly measured or explained. That reframing solved one problem, but immediately created another, more specific question. If high-altitude winds were genuinely distorting the signal, what, exactly, was generating those particular winds in the first place? That open question sat unresolved for 5 more years. The answer finally arrived using the exact same November 29th, 2024 near-spec dataset that produced the dark beads and star arm discoveries, published in 2026 in the Journal of Geophysical Research, Space Physics. A 16-scientist team, drawing on researchers from Northumbria University, Boston University, the University of Leicester, Aberystwyth University, the University of Reading, Imperial College London, Lancaster University, and the Johns Hopkins Applied Physics Laboratory, mapped the infrared emission from a specific molecule called trihydrogen cation, H3+ for short, which behaves in Saturn's ionosphere, essentially like a natural thermometer, its emitted light shifting in ways that directly reveal the surrounding temperature. This new measurement was roughly 10 times more precise than anything Cassini or ground-based telescopes had ever managed. A genuinely important detail, because prior estimates had carried uncertainties of nearly 50 degrees Celsius, almost as large as the actual temperature effect researchers were trying to measure in the first place. It's difficult to confirm a subtle, real signal when your measurement error is nearly as large as the signal itself. With that 10 times sharper measurement finally in hand, the picture became clear. Saturn's auroral heating, it turned out, is genuinely lopsided. One side of the planet's northern polar atmosphere reaches a temperature of approximately 480 Kelvin, roughly 207 degrees Celsius. The opposite side sits considerably cooler at approximately 400 Kelvin, or about 127 degrees Celsius. An asymmetry of roughly 80 Kelvin, rotating around the pole once every single Saturn day. And that rotating temperature asymmetry, it turns out, is the entire missing piece. A lopsided distribution of heat drives directional winds. Those winds, moving through Saturn's own magnetic field, generate electrical currents. And those electrical currents, in turn, help power the very aurora that originally produced the lopsided heating in the first place. A complete, closed, self-sustaining loop, confirming a theoretical model that had actually first been proposed all the way back in 2011, 15 years before this direct observational confirmation finally arrived. Lead researcher Tom Stallard summarized the entire finding in a single, memorable line. "What we are seeing," he said, "is essentially a planetary heat pump. The system feeds itself. Sit with the full timeline of this specific mystery, because it's genuinely worth appreciating. It began with strange readings in Voyager-era data in the early 1980s. It deepened through Cassini's confirmation, starting in 2004, that something genuinely odd was happening. It found a promising reframing in 2021. And it finally reached a direct, confirmed answer in 2026. A span of roughly 45 years, start to finish. Long enough for a researcher to have begun this exact puzzle as a graduate student and finally solved it as a professor nearing the end of their career. Here's where this particular story takes one more turn, and it's worth sitting with directly, because it captures something genuinely important about how real scientific discovery actually works. Rarely in clean, single, closed chapters, and far more often as one answer quietly opening a door onto the next question. While confirming the self-sustaining heat pump mechanism behind Saturn's rotation rate mystery, the same research team noticed something else in their data, something nobody had specifically gone looking for, and something that immediately contradicted a basic expectation built into decades of prior auroral physics. The hottest part of Saturn's polar region, roughly the band of latitude between 70 and 73 degrees north, precisely the zone where that dramatic 480 Kelvin temperature peak occurs, turned out to also have some of the lowest hydrogen ion density found anywhere across the entire observed field. In normal auroral physics, on Saturn and on every other planet with a magnetic field that's ever been studied, hot regions and dense regions are expected to track closely together. More incoming charged particles generally means both more heating and more ionization happening simultaneously in the same general location. Finding the hottest patch of atmosphere also registering as one of the least dense, in terms of the specific ions researchers were measuring, runs directly against that basic, well-established expectation. Two competing explanations have been proposed, and it's genuinely worth understanding both, because neither has yet been confirmed. The first possibility is mechanical. The same powerful winds responsible for the heat pump mechanism might simply be physically pushing ions out of the hottest zone faster than new ones can accumulate, actively sweeping the region clear even as it continues heating up. The second possibility involves a specific kind of incoming particle sometimes called electron rain. A steady influx of charged particles from Saturn's own magnetosphere that, rather than simply adding to the existing ion population the way typical auroral particles do, might instead be actively destroying ions faster than the ongoing auroral process can replace them. As of the most recently published research available, this remains genuinely, explicitly unresolved. Both explanations are considered live, viable hypotheses. Neither has been ruled in, and neither has been ruled out. There's something worth pausing on here in the specific rhythm of this particular story. A genuine 45-year mystery. Saturn's apparently shifting rotation rate was finally definitively solved in 2026. And the very same dataset that solved it immediately produced a brand new, equally unexplained anomaly sitting right at the center of the solved mystery's own most important finding. Science, done honestly, rarely closes a book entirely. It tends, instead, to trade one open question for another, each new answer revealing the next layer of the puzzle waiting just beneath it. Let's turn now to something that sounds, at first, like it should be one of the more straightforward things to measure about any planet. How fast does the wind actually blow? Saturn's equatorial jet stream is, by a considerable margin, the widest and most intense of any wind pattern found anywhere in the solar system. It extends roughly 70,000 kilometers from north to south, more than 5 times the entire diameter of Earth, forming a single, continuous band of extraordinarily fast-moving atmosphere wrapped around the planet's midsection. Peak wind speeds, based on measurements taken during the Voyager flybys of 1980 and 1981, have historically been cited at up to 1,800 kilometers per hour, or roughly 1,100 miles per hour. Here's a way to actually feel that number. 1,800 kilometers per hour is close to 1.5 times the cruising speed of a commercial jet airliner. Except this isn't a brief flight, and it isn't a single gust. It's a sustained, permanent, continuously circling weather pattern wrapped around an entire planet that has no solid ground anywhere to ever slow it down. But here's the detail that turns this from a simple, impressive statistic into a genuine scientific puzzle. These winds are not constant. They've measurably, significantly changed across the decades scientists have been tracking them, in ways that don't fit any simple, tidy explanation. A 2003 study, conducted by a planetary science team at the University of the Basque Country, found that cloud-level wind speeds had dropped substantially compared to the original Voyager-era readings from 2 decades earlier. Subsequent tracking using the Hubble Space Telescope found peak equatorial winds had slowed further still, down to roughly 1,100 kilometers per hour, or about 690 miles per hour. Nearly 40% slower than the original Voyager measurements. And yet, in 2015, researchers clocked a specific storm moving at speeds that hadn't been measured since the original 1980. 81 Voyager flybys. A sudden, apparently temporary return to the earlier, faster regime. More recent published estimates, from 2024 through 2026, again put peak jet velocities somewhere between 1,620 and 1,800 kilometers per hour, roughly back in line with the original Voyager numbers, about 1/3 the speed of sound. Slower, then faster again, then apparently back to where it started, across roughly 4.5 decades of intermittent measurement. And the researchers studying this directly, in their own published words, have been genuinely honest about the state of their understanding. There is, they wrote, as yet no theory capable of explaining the nature of this stream, nor the sources of energy feeding it. The same team noted that the jet's full vertical structure, and the reasons behind its apparent variability over time, have so far not been well characterized at all. There's a subtle but genuinely important complication buried inside all of this, and it connects directly back to the rotation rate mystery we just walked through in the previous section. Wind speeds on gas giants like Saturn are always measured relative to the planet's own deep, underlying rotation rate. The same rotation rate that, as we just discussed, turned out to be considerably harder to pin down than anyone originally expected, precisely because the radio signals used to measure it were themselves being distorted by high-altitude winds. Which means the rotation rate mystery from Section 10 isn't a side note to this section's wind mystery. It's the literal 0 point, the fixed reference baseline, that every single wind speed measurement on Saturn ultimately depends on. Get the rotation rate wrong, even slightly, and every wind speed figure built on top of it shifts along with it. There's one more recurring phenomenon worth including here, because it adds real texture to just how extreme Saturn's atmosphere can occasionally become. At these same equatorial latitudes, astronomers have periodically observed something called the Great White Spot, a storm large enough to visibly encircle the entire planet, bright enough to be seen from Earth with a good telescope. It has been documented only 6 times across roughly 150 years of careful astronomical record-keeping in 1876, 1933, 1990, and several subsequent occurrences since. A genuinely rare, genuinely enormous storm system, appearing on a schedule nobody has yet fully explained either. For comparative context, it's worth briefly setting Saturn's winds against the other gas giants of our solar system. Jupiter's winds run at roughly 540 kilometers per hour above its own baseline rotation rate. Uranus reaches approximately 900 kilometers per hour. Neptune, sitting at the very outer edge of the solar system, holds the overall speed record among all the planets, with winds reaching somewhere between 2,100 and 2,400 kilometers per hour, depending on which specific measurement you consult. Saturn, depending on exactly which decade's data you're using, sits in genuine direct competition with Neptune for the title of fastest sustained planetary winds anywhere in our solar system. An extraordinary distinction for a planet sitting so much closer to the warming influence of the Sun than distant, frigid Neptune. It's worth spending a moment understanding exactly why wind measurement on a gas giant like Saturn turns out to be such a persistently difficult scientific problem, because the difficulty itself tells you something honest about the limits of remote planetary observation. On Earth, meteorologists measure wind using a dense global network of physical instruments. Anemometers mounted on solid ground, weather balloons rising through the atmosphere, satellites tracking the movement of clouds relative to a fixed, unmoving planetary surface below them. Every measurement has a stable reference point to compare against. Saturn offers none of that. There is no solid surface to anchor any instrument to, and no fixed ground-level reference point against which cloud motion can be reliably measured. Every wind speed reported for Saturn is necessarily indirect, calculated by tracking the movement of visible cloud features against Saturn's own inferred rotation rate. The same rotation rate that, as we've now covered in detail, turned out to carry decades of hidden uncertainty, precisely because the radio-based method used to measure it was itself being distorted by high-altitude atmospheric winds. This creates a genuinely circular measurement problem worth sitting with directly. To measure wind speed accurately, you need an accurate rotation rate to measure it against. But part of what determines the apparent rotation rate, as researchers only fully confirmed in 2026, is itself driven by high-altitude wind activity. Untangling exactly how much of any given measurement reflects real, physical wind speed and how much reflects lingering uncertainty in the underlying rotational reference frame remains a genuinely active area of ongoing research, which helps explain why different decades of Saturn wind measurements have produced numbers that don't cleanly agree with one another, even when each individual measurement was conducted carefully and competently by qualified researchers. Add to this the simple fact that different observation campaigns, spread across more than 4 decades, have used different instruments, different wavelengths of light, and different specific cloud features to track. Voyager's brief 1980, 81 flyby snapshot, ground-based telescope campaigns in the early 2000s, Hubble's longer baseline tracking, Cassini's 13 years of continuous close observation, and now Webb's newest infrared measurements. And the honest picture that emerges is of a genuinely difficult measurement problem, tackled from several different angles over several different decades, producing a body of data that is real and useful, and still not fully reconciled into one single, agreed-upon, complete explanation. Let's turn now, for the remainder of tonight's exploration, away from Saturn's atmosphere entirely and towards something happening on one of its smaller, icier companions. Because James Webb's observations here may carry the most significant long-term implications of everything we've covered tonight. On November 9th, 2022, James Webb's NIRSPEC instrument observed something erupting from Saturn's small moon Enceladus, a plume of water vapor extending outward from the moon's surface by more than 6,000 miles, or roughly 9,600 kilometers. The full published study, led by Geronimo Villanueva of NASA's Goddard Space Flight Center and published in the journal Nature Astronomy in May 2023, described emission detectable out to an even greater distance still, approximately 10,000 kilometers, or the equivalent of 40 times Enceladus's own radius. To actually feel the scale of that number, it helps to remember exactly how small Enceladus itself is. The entire moon measures only about 500 kilometers, or 310 miles, across. Smaller than many individual countries here on Earth. The plume erupting from its surface, at its most extensive, reaches somewhere between 20 and 40 times the size of the Moon actually producing it. Imagine a fountain erupting from a source the size of a small city, spraying water vapor a distance greater than the width of an entire continent. Enceladus completes a full orbit of Saturn every 33 hours, remarkably fast, a consequence of orbiting relatively close to such a massive planet. As it moves, its continuous plume activity leaves behind a donut-shaped ring, or torus, of water vapor, tracing out its own orbital path around Saturn. Webb's data indicate that roughly 30% of all the water ejected by Enceladus's plumes stays trapped within this torus, continuously circling the planet, while the remaining 70% escapes outward entirely, helping to supply and replenish Saturn's broader ring and moon system, including its faint, diffuse outer E-ring, beneath Enceladus's icy, distinctively striped surface. Marked by a series of long fractures near its south pole, nicknamed tiger stripes for their visual resemblance to an animal's coat, lies a genuine liquid water ocean, estimated at roughly 25 miles, or 40 kilometers, deep, resting on top of a rocky seafloor. This subsurface ocean was first identified using data gathered by Cassini during its 13 years at Saturn, and James Webb's newer observations are now allowing scientists to characterize its chemistry in considerably finer, more precise detail than ever before. Lead researcher Geronimo Villanueva described the actual observational experience of watching this data come in with a memorable, almost disbelieving simplicity. The plume, he said, was so large that in Webb's data there was just water absolutely everywhere. Follow-up observations, awarded as part of Webb's second observing cycle to researcher Christopher Glein at the Southwest Research Institute, are now specifically searching Enceladus's plume for organic compounds, and for a specific chemical called hydrogen peroxide. A molecule of particular scientific interest, because it could, in principle, provide a considerably more potent source of metabolic energy for any potential microbial life than anything Cassini's earlier, less sensitive instruments were ever capable of detecting or ruling out. As of the most recent published research available, this search remains genuinely, actively ongoing. No organic compound and no biosignature of any kind has yet been confirmed. Here's a way to hold the pace of Enceladus's own activity in mind. At 33 hours per orbit, this small, icy moon completes more than 260 full orbits of Saturn in the same span of time it takes Earth to complete a single trip around the Sun. That donut-shaped torus of water vapor isn't a static, one-time event, captured and then finished. It's being continuously replenished and continuously reshaped multiple times over in the course of a single Earth week, happening, all the while, on a moon smaller than the round-trip driving distance between London and Paris, repeated 20 times over. It's worth pausing here to understand exactly why a moon this small has become one of the single most closely watched objects in the entire search for life beyond Earth. Because the reasoning connects several genuinely separate lines of evidence into something considerably more significant than any one discovery on its own. For life as we understand it, at a minimum, you generally need three things: liquid water, a stable source of chemical energy, and the right basic elements. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, available in a usable form. Enceladus, based on everything Cassini and now Webb have measured, appears to genuinely satisfy the first of these requirements beyond serious doubt. A liquid water ocean, kept from freezing solid by tidal heating generated as Saturn's own powerful gravity continuously flexes and stretches the moon's interior during its rapid 33-hour orbit. Cassini's earlier fly-throughs of Enceladus's plumes already detected simple organic molecules, along with molecular hydrogen. A molecule of particular interest because, on Earth, certain forms of microbial life are known to derive usable metabolic energy directly from the specific chemical reaction between hydrogen and carbon dioxide, a process called methanogenesis. Finding hydrogen in Enceladus's plume was already a genuinely significant piece of evidence, suggesting the Moon's subsurface ocean might, in principle, contain an active source of chemical energy of exactly the right kind. What Webb's newer, more sensitive observations are now specifically hunting for: organic compounds in greater detail, and particularly hydrogen peroxide, would meaningfully strengthen this picture further still if found. Hydrogen peroxide, in particular, matters because it can serve as a considerably more potent oxidant than some of the chemistry Cassini was previously able to detect, potentially supporting more energetic metabolic pathways than simple methanogenesis alone would allow. None of this constitutes evidence of actual life. It's genuinely important to be precise about that distinction. What it represents, instead, is an increasingly detailed, increasingly complete picture of the specific chemical and physical conditions inside Enceladus's ocean. Conditions that, piece by piece, keep turning out to be more genuinely conducive to the possibility of life than researchers initially expected when Cassini first detected the Moon's plumes back in 2005. Each new piece of confirmed chemistry doesn't prove anything about biology directly. It simply narrows, very slightly, the list of reasons Enceladus's ocean couldn't support life, without ever actually closing that list entirely. Before we move toward tonight's closing reflection, it's worth gathering everything we've covered and sitting with exactly how much of it traces back to a genuinely small amount of actual observing time. Every major discovery in tonight's exploration: the dark beads embedded in Saturn's aurora, the star-shaped pattern with its two missing arms, the resolution of a 45-year-old rotation rate mystery, and the brand new ion density anomaly that discovery immediately revealed. All of it came from a single, continuous 10-hour observation conducted on a single day, November 29th, 2024. Add to that one earlier baseline study from November 2022, and one additional Enceladus observation from earlier still, and you have the complete observational foundation for essentially everything tonight's story has covered. That is an extraordinarily small amount of total dedicated observing time to have meaningfully reshaped this much of Saturn's entire scientific record. A record that, by the time these observations were made, already represented 46 years of direct spacecraft study, going all the way back to the first Pioneer 11 flyby in 1979. Saturn has been visited by 5 separate spacecraft missions. It was watched continuously, in extraordinary detail, for 13 unbroken years by Cassini alone. It sits, tonight, exactly where it has always sat, roughly 900 million miles from Earth, entirely unaware of and entirely indifferent to any of the careful human attention currently being paid to it. And multiple credentialed research teams, publishing their findings in genuinely rigorous, peer-reviewed scientific journals, currently describe core features of its atmosphere using a single, honest, recurring word: unexplained. There's something genuinely worth sitting with here, now that we've walked through the full scope of what James Webb actually found. We tend to imagine scientific progress as a kind of steady, forward-marching completion, each new discovery filling in one more piece of an eventually complete picture, each better instrument bringing us measurably closer to a finished, fully understood universe. And in a great many ways, that really is how science works. Webb's observations of Saturn did genuinely solve one of the planet's oldest, most persistent open questions. The 45-year mystery of its own apparently shifting rotation rate, finally, definitively resolved in 2026. But sitting alongside that single closed chapter are at least 4 others that remain genuinely, honestly open. The cause of the dark beads. The reason 2 of the star pattern's expected 6 arms are missing. The full nature of the vertical connection, possibly linking Saturn's deep clouds to its outer ionosphere. The precise cause of the newly discovered ion density paradox found hiding inside the very data that solved the rotation mystery. the complete physical explanation for the equatorial jet stream's decades of unexplained speed variation. And, quietly waiting in the background, the still unanswered question of exactly what, if anything, Enceladus's ocean might be capable of supporting. There is a particular kind of humility worth genuinely appreciating in this. Saturn is not some newly discovered, dimly understood object, glimpsed for the first time at the very edge of our instrument's capability. It is one of the most thoroughly, patiently, expensively studied objects in the entire solar system. A planet that has already received 5 dedicated spacecraft missions, 13 years of continuous close observation from a single orbiter, and now the additional scrutiny of the most sensitive space telescope humanity has ever built. And it remains, tonight, genuinely capable of surprising the very people who know it best. There's a specific way of thinking about this that the researchers involved in these discoveries themselves seem to hold, and it's worth adopting as our own closing thought for tonight. The universe doesn't owe us a fully solved solar system, tidily completed and filed away. Saturn, sitting quietly in the night sky exactly where it has always been, visible to the naked eye from Earth on any clear evening, is still, after nearly half a century of the closest human attention we've ever managed to give it, capable of handing working scientists a result they genuinely cannot yet explain. That isn't a flaw in our understanding or a failure of our instruments. It's precisely what makes the continued looking worth doing at all. Picture it, one last time, before we close tonight. Somewhere above you, on any clear night, sits a planet that human beings have now been examining, up close, for nearly half a century. 5 spacecraft have visited it. One of them spent 13 unbroken years in its orbit, watching every visible change, before finally, deliberately, becoming part of the planet itself. And in the space of a single 10-hour observation, gathered on one ordinary day in November 2024, that same planet quietly handed the most advanced instrument ever built 4 or 5 genuinely new mysteries, layered at different altitudes, in different physical regimes, connected to each other in ways we can currently only guess at. A chain of dark patches, embedded in glowing curtains of aurora, stable for hours, then slowly drifting, for reasons nobody can currently name. A star-shaped pattern, missing exactly the arms it should have, hundreds of kilometers below. A 45-year rotational mystery, finally closed, immediately replaced by a new one hiding inside its own solution. A wind stream wider than 5 Earths laid end to end, blowing at 1/3 the speed of sound, with no accepted theory explaining where its energy actually comes from. And on one small, icy moon, barely the size of a modest country, an ocean of liquid water, spraying itself into space in a plume 40 times its own size, quietly holding chemistry that might, or might not, someday turn out to be capable of supporting something alive. We are not looking at a solved solar system. We never really were. We are looking, tonight, at a planet that has been patiently watched for 46 years, and that continues, patiently, to watch us back with its own quiet indifference, offering up exactly as much of itself as our instruments are currently capable of receiving, and holding the rest, for now, just out of reach. That isn't something to fear. It's something worth genuinely treasuring. The knowledge that even here, in our own solar system, on a planet we can point to with our own eyes on any clear night, there is still, honestly, more to find. Tonight we explored why James Webb's recent observations of Saturn have left working scientists using a word you rarely see in peer-reviewed research: unexplained. We found a planet already studied for 46 years by 5 spacecraft, including 13 unbroken years of close observation from Cassini. A genuinely thorough scientific baseline against which everything that followed became considerably more striking. We found dark, bead-like patches embedded in Saturn's aurora, stable for hours yet slowly drifting, described by the researcher who found them as completely unexpected and completely unexplained. We found a star-shaped pattern hundreds of kilometers below those beads, missing 2 of its expected 6 arms, hinting at a vertical connection through Saturn's atmosphere that has never been directly confirmed. We found a 45-year-old mystery about Saturn's own basic rotation rate, finally resolved in 2026 through a self-sustaining planetary heat pump. And, hidden inside that very resolution, a brand new anomaly nobody had gone looking for. We found an equatorial wind stream wider than 5 Earths, blowing at 1/3 the speed of sound, that researchers themselves admit has no accepted theory explaining its energy source, its structure, or its decades of unexplained speed variation. And we found, on the small moon Enceladus, a plume of water reaching 40 times its own source's size, hiding an ocean whose full chemistry, and whose full potential to support something alive, remains an active, ongoing, unresolved search. None of this is a story about failure. It's a story about honesty, about what it actually looks like when some of the most capable scientists alive, using the most sensitive instrument ever built, look as closely as current technology allows at something we already thought we understood, and tell us, plainly, exactly how much we still don't. Sleep well tonight, knowing that a planet you can find with your own eyes, on any clear evening, still holds mysteries the best minds and the best instruments on Earth have not yet solved. And that somewhere, right now, a team of researchers is quietly, patiently working to close that gap, one honest, we don't know at a time. Good night. And rest well under a sky that is, even now, after everything we've learned, still keeping some of its secrets.